Hello and very good evening. My name is Shaunak and welcome to today's session where we are going to learn what is called Lagrangian mechanics. Now, in the yesterday's output, Rudra si namaskar. Rudra, can you tell me that my voice is absolutely clear? Because yesterday there was some disturbances, there was some noise which was coming. So I'm just holding my mic a little bit closer to my mouth so that things become a little bit clear. So Ram Bharos, hello, and Rudra, hello. And can anybody tell me yes or no? The voice is clear. Okay, thank you. So voice part is clear. Voice is clear. Wonderful. So in today's session, we will try to cover what is the most important and fundamental principle of physics, which are actually seen to be extended in biology, economics, even in economical science also. That is the concept of Lagrangian. And we will also try to cover and understand what are called Lagrangian equations, the Euler Lagrange equation. And I'm sure that although it is a little bit mathematical, I'm going to make it super easy and you're going to enjoy. And there are some fascinating histories also involved in this. So, first of all, on a very easy note, although it is very deep and philosophical, let us understand what is a Lagrangian. Now, here you can see that in general, Lagrangian actually means kinetic energy and potential energy. Before starting, I would like to tell you that the type of Lagrangian we are talking is a classical Lagrangian mechanics. So the T is a classical kinetic and V is a classical potential energy. We are not considering anything relativistic in today's session. So yes, Lagrangian can be extended to relativistic and quantum theory also, but currently we are not looking there. Now, here you see that when we talk of the Lagrangian as a whole, T minus V, there are a few things that we need to understand that L or the Lagrangian is a physical quantity. It has nothing, it is not a physical quantity, and it has basically a mathematical quantity. So, to be honest with you, you really cannot see a Lagrangian. You cannot see that it is doing some kind of a physical, I would say, a physical outcome. So, this is purely a mathematical quantity. Okay. And sometimes also it is written as a curly L, which I have written at the bottom. And we can tell that the Lagrangian is basically the best path or the most natural way the system will move using the principle of least action. Now, here I would like to take a pause because when we talk of a system evolving in a natural way, remember that these things can be further extended in what is called in any branch of science. Because science is not only physics or mathematics, but any kind of a system. It can be thermodynamical system, it can be economics, it can be gene evolution or a biology also. But if we can use Lagrangian in a proper way, it actually shows how a particle or how a system evolve in a very natural way. And that is why you will see that in many of my videos in this what we called, just a second, in what we called is the Einstein-Hilbert action. In many cases, I have actually written that it is Einstein field equations do have a limitation, but Lagrangian has no limitation because this is the most natural way in which things can evolve. So if we can calculate Lagrangian of any system, it gives a wonderful way to move ahead. Now, if we talk of, say, for example, anything which is physical, I would like to show you this one. Now, Hamiltonian mechanics or Hamiltonian, we can say, is a very important principle and it props up mostly in quantum mechanics. So, Hamiltonian is something which represents a total energy. So, if you talk of a physical system as a whole, which is not the Lagrangian, Hamiltonian is much more physical because it represents what is the total energy. The hat on the T and the V actually shows that these are basically what are called, it is an operator, and that is why we put a hat on the top. We will deal with this operator someday or the other. But what it shows is that Hamiltonian basically deals with the total energy of a system. It is used in Schrodinger's equation and in various other ways. So in contrast to Lagrangian, Hamiltonian is a physical quantity. Now, I always wondered, and I'll always try to give a understanding that in Lagrangian mechanics, why we are using this T minus V. I understand that in case of Hamiltonian, we use a plus because we need to denote what is called the total energy. But why we are using T minus V? Now, you see that in this part of our session, I'm trying to tell you that L equals to T minus V is something, I will come to the analogy part, but it actually shows the action principle. Now, action principle is the same action principle which we learned in our classical mechanics. It is the same thing. So what happens is that, as you can see, S is basically the action, and it actually tells how the Lagrangian changes over time. If we take a particle which is starting at T1, we start analyzing the system at T1 and how it finishes at T2. And the value of S, which I have written at the bottom, I could have got a board and I could have written those things. But anyway, the value of S, which is the action principle, it changes if we get a Lagrangian, which also changes. And the Lagrangian changes when we have different kinetic and potential energies. So L is how the Lagrangian changes. dt is the differential in time. The integral actually calculates the entire path of a particle starting at position T1 and moving up to position T2. And we get the action principle as a scalar quantity. Scalar means it is a singular quantity, which makes our calculations even easier. And this S changes as the Lagrangian changes, and the Lagrangian changes if we get different types of kinetic and potential energy. So this is basically the core of the Lagrangian, which is based on the principle of least action. Now, also you see here, I have given a kind of a diagram. So here you see that the particle starting from T1 and moving up to T2, it can take a S1 path, it can take a S3 path, it can take a S4 path, but it actually takes one path, which is the S1. Why it takes so? Because it is the principle of least action. That means actually what happens, the kinetic and the potential energy is balanced over here. And that is why you see I have given that it states that the system motion between two states is such that the action is minimized. And this is so fundamental. For example, when I am dealing with the college students, that which job they should join, either a research or application based quantum job, quantum mechanics or quantum computing, I always see that the human mind also follows this principle, that given the salary, given the location, given the job, given the type of energy that you have to do, human beings also follow the principle of least action. Why? Because you will only take that job or you will do that thing where you will find that you get the minimum amount of understanding, where the understanding is absolutely minimal. That means your energy is perfectly balanced. So this is what actually happens in case of this. So S equals to the integral of T1, T2 and L dt. So as soon as we substitute L, that is T minus V, we get T minus V dt. So what we do is that after deduction of kinetic and potential energy, what is left is actually the principle of least action. This is why it shows T minus V. I will give you further examples which are going to make this analogy clear. Now here you can see what I have done is that I have taken L equals to T minus V. Why I have taken L equals to T minus V? Because we can measure how freely the system moves. So it balances the interplay between kinetic and potential energy. Kinetic T, it actually drives the motion, and V is constraints of the motion. And also it is important to know that from the Lagrangian L equals to T minus V, what we get is the Euler Lagrange equation. We will look what is an Euler Lagrange equation. And this Euler Lagrange equation again returns us back to Newton's second law. So if you take a particle, which on the right hand side is this yellow circle, right? And if you are moving this particle, if the kinetic energy is more than potential energy, the motion is free. And if the potential energy is more than kinetic energy, that means the motion is constrained. That means we have problem. Okay. This will make things a little bit clear. Now, I want you to imagine that you are running a race. Okay. For example, you're running a race. Now, when you're running a race, your performance, that means how far you and how fast you can run, depends on two things. One is your energy to run. This is the kinetic energy T, which drives your motion and helps you make progress. And the second one is the resistance, is the potential energy V, which slows down your motion due to friction, hills, or wind, or whatever. So your actual progress depends on the difference between your energy and the resistance. So we can say progress equals to effort minus resistance. L equals to T minus V. So if your effort is much greater than resistance, you move forward. If your effort is only slightly greater than resistance, you still move forward but more slowly. And if your effort equals resistance, you are stuck, then there is no motion. And if the resistance is greater than your effort, you actually push backward. So the Lagrangian is the net progress, which reflects the balance, what drives the motion, kinetic energy, and what resists it is the potential energy. So, and in contrast to that, Hamiltonian actually shows the addition of two energies, T plus V. So I hope this part till now it is clear, and from here you can understand that why there is a minus sign. I will show you a further analogy which is going to make the concept of Lagrangian more clear. Here is the a kind of an analogy, the same one. So the minus sign is there because the motion determined by how much energy you have left. So adding your energy and resistance doesn't tell how far you will go. Subtracting resistance from your energy tells you what is available for progress, which is the key for determining the motion. So again, it is the same thing, that if your effort is much greater, this is so. If your effort is only slight greater, then resistance is move forward. And if your effort equals the resistance, then you are stuck in the motion. There is no motion. And that is why you see that when I showed this part of the here, del S equals to 0, what does that mean? It means it has got the lowest value. That means it is absolutely minimal where it is going. So that is why it is called L del S equals to 0. Now this is actually why it is. So from here we can quickly move on the next part of our understanding, that this L equals to T minus V, what it actually shows is actually the minus sign. And subtracting resistance from an energy actually tells what is the available progress. So this part, I hope it is clear for those who are watching the video, that what is a Lagrangian, why we use the minus sign, and this minus sign actually subtract your resistance from an energy and tells how much you are progressing. And this progress is actually determined by what is called the equations of motion. Okay, now we come to how do we calculate a Lagrangian? Now here I would like to take a pause and I will try to explain. Those who have watched my videos, or if you're reading a book on quantum field theory, the concept of Lagrangian also comes over in quantum field theory. Why it comes over here? Because Lagrangian, as I told you, is not only restricted to what is called the physics or classical physics or the equations of motion. Even in quantum field theory, it can further get extended. Now, in quantum field theory, we get something which is called a simple harmonic motion. Okay, so simple harmonic motion is something which we are going to see over here, although we won't make things so much complicated. But what we are going to do is that we are going to take a spring. Okay, so here you see that there is a spring which is a frictionless, and it is moving in the direction which is this direction S, X direction. I'm so sorry. It is moving in the direction which is X. Now here you can see that there is a X with a dot, and this is just a notation which makes the mathematics look easier. So you know that the dot represents d by dt. So if we plug in L equals to T minus V, and if we know that kinetic energy is half mv squared, which is from the Newtonian mechanics, and this mass is, the V is basically the derivative of the position. We know V equals to dx by dt, and from there we can easily write half mx dot squared. As I told you, dot is basically d by dt. So if v equals to dx by dt, which is equals to x dot, automatically t equals to half mx dot squared. So x dot means the rate of change of x with time. That means how fast the thing is moving. So this is basically how we calculate what is called the kinetic energy. Now you see, similar way we calculate the potential energy. So potential energy is what, in case of a spring, we know if we apply the Hooke's law, it is simple, F equals to minus kx. So the potential energy stored in V equals to half kx squared. And here you can see x is the displacement and k is the spring constant. And we know that the work done to compress the strain is basically potential energy is the integral of f dx. So if we substitute Hooke's law, minus kx dx equals to times dx, then it becomes half kx squared. So this is how we actually calculate the potential energy. Hold on. This was the kinetic energy calculation. This is the potential energy calculation. Now, we also need to know that how do we calculate the Lagrangian after calculating the integral, the kinetic and the potential energy. Now, in order to do that, first we also need to understand that how the potential energy is stored in a spring. Now, in order to do that, you see that to find the potential energy, what we do is that we add up or integrate the work done due to stretch or compression. So simple, we do F equals to minus kx, which is the Hooke's law, and it tells that the force exerted by the spring is proportional to how you stretch or compress it. The spring always tries to return to its original position, and that is why it is negative. That means it opposes the direction. I cannot show you the animation, so it comes back. So K is the spring constant, and which tells you how the spring is stiffer, and X is the distance you stretch the compress the string. And once we substitute this F equals to minus Kx, we get this PE equals to integral of F dx. Yeah, hi, hello. Now from here, what we find is that the calculation of the Lagrangian. Now here you can see I have just put up this part. This man who is pushing this it actually means the harder you push, the further you move in it, and the work done is more. So that is why this animation. So substituting this F equals to minus kx leads to PE is equals to integral of F dx. Okay, this is simple. Now from here, what we get is this. We substitute, we get this one. This means that we are calculating the total work needed to stretch the spring from its natural position to x equal to 0 to a new position. And if we solve the integral, we get this kind of a value, which is PE equals to V equals to half kx squared. Now here you can see if we substitute the values, now you see if I get kinetic energy minus potential energy, T is the kinetic energy. Okay, what is the kinetic energy? Here it is. We have calculated this. Okay, this is half mv squared, half mx dot squared, and the potential energy is minus half kx squared. And here I have just substituted it, and we got the Lagrangian. Okay, so this is a very simple way, of calculating the Lagrangian. Although there are many more methods of calculating the Lagrangian, but using the spring constant and using the spring value is one of the most easiest part of calculating the Lagrangian. Now Lagrangian has got many other usages, but first of all, using this Lagrangian only, what we will look in the most fundamental part, which is called the Lagrangian and the Euler Lagrange equations. Now, Euler Lagrange equations, although it seems to be complicated, but they are fairly easy. I will make it simple for you. And remember that the Euler Lagrange equation, as we will look in today's session more deeper, it is nothing but Newton's laws of motion. Okay, but Newton's laws of motion has certain restrictions. Restriction because in case that things become complex, or we get double pendulum, we get field type extensions, Newtonian laws becomes difficult. I mean to say, again, it is not wrong, but it becomes very difficult and difficult to calculate. So we use something which is called the Euler Lagrange equation, which makes things very clear. But here what we would see is that we will just calculate the Euler Lagrange equations using this formulation. Now here you can see, I will just explain what do I mean by this slide, this slide. Now here you can see, first of all, we calculate the Lagrangian, what we have done, the spring mass system. Okay, you can see x dot is the velocity, x is the displacement, m is the mass, and k is the spring constant. The second step, what we are doing over here is that we are taking the derivative of L with respect to x dot. Simple. We are computing partial L by partial x dot. So we first take the derivative of L, and we know that the first term, half mx dot square, only depends on x dot. So we get partial L by partial x dot equal to mx dot. Next, what we are doing, we are computing d by dt. So we take the time derivative of mx dot, and the moment we take the time derivative of x dot, what we get is this one, x double dot equals to d square x by dt square. You all know what x double dot is. It is a second derivative, and from here you can see that we are getting what is called the acceleration. So once we get this acceleration, we move to the next part, where what we are doing is that we are computing partial L by partial x. So we take the partial derivative of L with respect to x, and we get this value. And we know that the spring value, that is half kx squared, only depends on x, which we have seen earlier. And we get this value, partial L by partial x equals to minus kx. If we put this into the Euler Lagrange equation, which we will explain later, just let us understand that there is a Euler Lagrange equation. It becomes mx double dot minus of minus kx equal to 0. Minus minus makes it plus. So we get mx double dot plus kx equals to 0. And we get from there, if we take x as common, we get this one, which is just simply the equations of motion. Very simple calculation. I have done nothing extraordinary, but I have just put the values and I have calculated. So these are mx double dot, these are equations of motion. And from these equations of motion, what we understand, that the net force is equal to force exerted by the spring. Now, at this point of time, you might be thinking that what is so extraordinary? We know that the net force is equal to force exerted by the spring. Then why do we go all the way around and plugging in the Euler Lagrange equations and getting all these values? We will soon understand this. We will definitely going to understand this. But before that, I will like to show you the next part. Here you can see that this x double dot is nothing but acceleration. Okay, this x double dot is basically nothing but the acceleration. And this from here, what we get is that mx double dot actually represents the inertial force. Okay, and in differential equation, and this actually tells that the acceleration x double dot of the mass is proportional to the displacement. So this is, I mean to say, this negative is basically a hallmark. This is something very important of simple harmonic motion, where a restoring force always acts and brings the system back to equilibrium. So here you can see that minus kx explicitly states that the acceleration of the mass is proportional to the displacement, but in opposite direction. Now, here comes the most important question, which you might be thinking, that why do we at all need that? I was talking that why do we need the Lagrangian mechanics to do, and what is the usage going all the way around and putting up the Lagrangian values in this? So here you can see that, okay, let me tell you in this way. When we are dealing with very small particles, there are very small particles, we can definitely use what we call Newton's laws of motion. But the problem is that when there are many particles, when the geometry and the entire system becomes very complex, then calculating each and every particle wise, all the f equals to ma and the derivatives become very difficult. So as you say, for example, if I take this one, and if I tell that how many dots are there in this box, okay, or for example, if I take this piece of shit, if I take this piece of sheet, this one, and if I take that, tell me how many points are there in this sheet, in this paper, then you need to calculate each and everything, which becomes very difficult. So what the Lagrangian tells, that instead of calculating these dots on this paper, we calculate what is called the total energy. So we calculate the total energy. And if we get the total energy, what happens is that calculation becomes much more easier. So here you see, I have told that it actually uses the total energy. And total energy calculation becomes much more easier. Okay, so in some systems, motion is described by generalized coordinates, not by typically angles, for example, polar coordinates, etc. Lagrangian mechanics provides a framework that naturally adapts to any coordinate system. Also, you will see that there are molecular dynamics, plasma dynamics, quantum mechanics, field theory of relativity, okay, curvilinear coordinates. All these things actually make things much more complex. So multiple degrees of freedom, forces which are not known. Are we going to deal with those things? So these make things much more easier. So quantum mechanics, for example, Newtonian mechanics breaks down and the principle of least action takes over. So how do we do that? Okay, field theory of relativity. When dealing with fields, for example, electromagnetic, gravitational, or relativistic forces, Lagrangian mechanics generates naturally to Lagrangian field theory. For example, double pendulum or robot which has got arms, we cannot handle it with Newtonian mechanics. Coupled systems, for example, force-based methods, etc., very difficult differential equations. So all those actually boils down to one point, that we need to know Lagrangian, so that instead of calculating each and every point of a test particle, what we can do is that we can calculate the total energy. And that is why I was constantly telling those who are interested in Einstein field equation and general theory of relativity, Lagrangian and the Euler Lagrange equations are used in Einstein Hilbert action. You can go to my video in this channel and the other channel. So you will see that how scalar quantities actually helps us to adapt many different things. So it becomes very easier. So here is a quick summary of what we have learned till now. We are not done yet. So you can see that we learned what is a Lagrangian. It is a mathematical entity, nothing physical. I compared that with an analogy. If you're running a race, then your kinetic energy, that is the total energy, and the resistance, if you subtract this, then what we get, that ultimately where you land up. It uses the principle of least action. That means basically the particle will use the least possible action. And also we calculated what is a Lagrangian using the spring constant. And we also saw here that from the Euler Lagrange equations, this is nothing complicated, but it actually gives what is called the Newton's equations of motion. And we do that because here on the right hand side, you can see it is easier. There are a lot of complicated systems which happens, and that is why the things become easier to calculate, because we don't have to deal with individual particles. Now we come to the next part. Is it impossible or just difficult to figure out expression or constraint force? No, it is not impossible. A very good question, Chudamani. It is not impossible, but just difficult. But that difficulty, Chudamani, when it comes to so many degrees of freedom, double pendulum, triple pendulum, relativistic motions, many particle system, it almost becomes impossible. So if you say that, can I walk from India to Brazil? Yes, I can. It is possible. Okay. But because of the difficulties, we say that it is very difficult. I hope you could. Just give me a short break. I'll just have a glass of water and we will come to the next part. How are you enjoying today's session? Any feedback? I hope you are all enjoying. Okay. Okay, we come next to this important part. What is the Euler Lagrange equation? Just a quick note for everyone. This might be a little bit mathematical, but don't worry, I am here and my earnest effort is to make the mathematics super easy and super simple. Okay, so I will just make things very simple for you. Okay, the Euler Lagrange equation looks something like this. Don't worry, it has got a lot of partial derivatives, but I'm going to make it easier. So overall, what we can say in general, that if you are trying to minimize or maximize a quantity, for example, time or energy, that depends on the shape of a curve or the behavior of a function, the Euler Lagrange equation gives us the rule that the function must satisfy to achieve this. That means that it actually tells the shape or behavior that what it should have in order to satisfy a function. You can say it is like an instruction for finding the optimal path or the best shape. Okay. Now, obviously, this L equals to t minus v, yes, absolutely, you're right. That is the Lagrangian. So the Euler Lagrange equation gives us a rule that the function must satisfy, and it will take you that in which shape this curve will go, or what is the optimal path, where this optimal path actually leads to. Now, I often see when I teach to students, they really don't know what is this. I mean to say, why this d by dt? Why do we need this? Why do we need to study? And why are those complex differential equations? And we say that the necessity is the mother of invention. Yeah, total energy means T plus V. Yeah. So we say that the necessity is the mother of invention. And here I would like to tell you that here this is something which is, there is a very, very interesting history, a very fascinating history. And I hope that this will give you motivation to learn what is called Euler Lagrange equation. Now, in the history of physics, there is something which is called a Tautochrone problem. Okay. Now, what happened is that the word taut, oh sorry, it is not visible. Actually, tauto means same, and chron means the same time. So tautochrone actually means something which is happening at the same time. Now, we know that Johann Bernoulli actually posed a challenge in physics in 1696. Okay, so what it tells that if you imagine a frictionless bead sliding down a wire, no matter where you release it on the curve, it will reach the bottom in the same amount of time. Now, this curious phenomena intrigued many scientists, and solving this problem was not a very easy task. Okay, so if you get a bead around this, okay, now if you release this, it is going to come down the way it comes down. So that is what is called the problem. And as you can see that an Italian mathematician, physicist, and astronomer, which later naturalized as Leonhard Euler and D'Alembert, Lagrange actually succeeded Euler as the director of mathematics at the Prussian Academy of Science in Berlin, Prussia, where he stayed over 20 years, producing many work. And from there, what we got is the Euler Lagrange equation. So what was the problem? Let us identify the problem. The problem is that to find a curve that ensures the ball takes exactly the same time to reach the bottom, no matter where it starts. It might start at the bottom, it might start at the beginning, wherever it will start. So this was basically the problem, that what shape the curve or the ramp would be so that the ball takes the same amount of time to reach the bottom, no matter where it starts. Okay. Now here is this is something I sometimes I have told this. Now what happened is that during that time Lagrange was only 19 years old, and he actually sent this problem to Leonhard Euler. And this book, The Tales of Mathematician and Physicist, it quotes that on October 10th, 1759, when Leonhard Euler received the equation of Lagrange, although he has already solved it. Now remember, Euler has already solved it, but what a great personality he is. He wrote that the importance of the question motivated me to the point this. And he told that I decline to conceal this until you publish your results, since you in no way do I want to take away from you any of the glory that you deserve. This is such an important phase. That means Leonhard Euler actually gave Lagrange to publish his equations, although Euler has already published it. Now, I don't know whether you have seen my short in this channel, on this channel Physics for Students, that it was just opposite of Carl Gauss. We know him as a great mathematician. But when Janus Bolyai sent a set of equations that he has discovered, what is called the non-Euclidean geometry, Gauss declined that. And Farkas Bolyai, who was Janus Bolyai's father, he told that, I don't think that your son has done a great job because I have already published it. But history tells that Gauss has never discovered non-Euclidean geometry. It was Lobachevsky and Janus Bolyai. But anyway, it shows the genius of Leonhard Euler, not only as a mathematician, but it tells that how great he as a person he was. And that is how the Lagrangian mechanics or the Euler Lagrange equation was actually born. Okay, so let us find out that what was the problem quickly. I won't go much of the details. The challenge was that to identify the exact shape of the curve and proving mathematically that the curve works for any starting point. So the role of the Lagrange equation is to solve the mathematically the time of descent, that means t, is expressed as a functional in terms of the curve. Now, remember, there is a difference between a function and a functional. Functional represents the total time taken by the bead to start. And here you can see the time of the bead has been calculated as this big one. Okay, where we can see that the first term is accounting for the curve's length and the second term gives the speed or the height. So what we can understand is that the Euler Lagrange equation is a powerful mathematical tool from the calculus of variations. The quantity to optimize is the time taken to the ball slide down the curve. Using the principle of least action, the Euler Lagrange equation derives the condition that the shape of the curve must satisfy for the time remain. And the equation was applied to the motion of ball under gravity, taking into account the relationship between position, speed, and time. So as you can see here, I have mentioned the time descent as a functional. Okay, now we come to, so I will quickly glance through this. This is something which is called the functional versus function. Functional considers the entire shape of the curve rather than a single point, and that is why it was very complex. Function is just finding a particular point. So the solution, what it got is a cycloid. Okay, so you know what is a cycloid is, looks like this. So that is why it shows that ultimately the solution comes to be a cycloid. Okay, so this is how the Euler Lagrange equation. So the basic foundation was to find out the problem and find out the solution, and the solution was not a straight line, not a curve, not a hyperbola, but what is found is that it is a cycloid. And this actually shows the nature of the problem, that it was proved that the cycloid is the only curve where a ball sliding under gravity takes the same time to reach the bottom. So we got the time integral, the Euler Lagrange equations, and the solution to the curve. Now here I would like to tell you, you must have noticed my another video which is called the Brachistochrone problem. Do you know what is a Brachistochrone problem? This was solved by Isaac Newton. And this was given as a challenge again by Bernoulli, and Leibniz also could not solve it. And I have made a video where you will see Bernoulli later told that I can recognize the lion by its claw. Overnight, Isaac Newton solved this problem, the Brachistochrone problem. It is similar to that, but it is not exactly like that. So what we came out that the Euler Lagrange equation actually came out of this Tautochrone problem. And using this equation, what we find is that this curve, that is a cycloid, perfectly balances the effects of speed and distance. So this is how the problem actually was born, and that is how the solution also actually came. Okay, now we will move in understanding what is called the Euler Lagrange equation. First, we will just get a basic understanding, and then we will go step by step in understanding what the equation looks like. Now, first you will see that this part. Okay, let me explain you, although it is written here, but I would like to explain this part. Now, here you can see the first thing what we see is that d by dt. First, let us concentrate on d by dt. It is simple calculus, okay? And this is the total time derivative of something which is called a generalized momentum. Now, here I would like to take a pause. Now, remember that in Euler Lagrange equation, there are three things which will come: generalized coordinate, generalized velocity, and generalized momentum. Now, why it is, I will come to that part later. Remember that coordinate velocity and momentum, which is there in the general Newtonian mechanics, doesn't work over here, because we need to generalize. As I told you, Lagrangian is a generalization of kinetic minus potential energy, so that things become much more easier. We deal with energies. Here in Euler Lagrange equation also, we have to deal with something which is called generalized. So don't worry, I will tell you what is generalized momentum. But at the moment, let us understand d by dt is nothing but it is the total derivative of the momentum. That means it measures how the momentum changes with time. Q is the generalized coordinate. Again, I will come to that later. So understand that for a pendulum, Q could be the angle of displacement. So it represents generalized coordinate, which is a variable to describe any configuration, anything of a system. Okay, partial L by partial Q. This is a generalized force. That means this term is the partial derivative of the Lagrangian with respect to generalized coordinate. And Q dot is the generalized velocity. It is simple, the velocity which we know, dq by dt is the time derivative of qi, because it is representing the velocity associated with a generalized coordinate. So everything actually changes. Momentum becomes generalized momentum, velocity becomes generalized velocity, and force becomes generalized force. So what we can tell from here, you can read the bottom part, that it tells that how a system evolves by stating the rate of change of generalized momentum is equal to the generalized force acting upon it. So you can basically tell that the equation tells that momentum is equal to force. Okay, in a very simple manner. I mean to say, but it carries a lot of partial derivatives, etc. So from here, if you move to the next part, you can see from here what we say, that the Euler Lagrange equation actually balances force in a dynamical system. So you can imagine the left hand side actually represents the rate of change of momentum. We should say generalized momentum, and the right hand side represents generalized force. So the equation actually is nothing but it tells that the change of momentum equals the force acting on a system, and this is something equal to F equals to ma in classical mechanics. Okay, but because of the complexities of the system, coordinates, fields, etc., we get all those things. Now I would like to explain to you that once we are telling generalized, why do we need this generalization? I mean to say, there should be a problem. Without a problem, why will we crack our head to make a new invention in mathematics or a new discovery? So first, let us understand that in case of Newtonian mechanics, we select coordinates like x, y, and z. But in many problems, you will see that x, y, and z does not work. For example, a pendulum which is moving in an arc, instead of x and y, it is easier that we choose one single angle, theta, and this theta can actually solve a lot of problem. Also, you will see many physical systems. For example, what we saw, the Tautochrone problem, a bead constrained with motion, okay? Force constraints, which can be very much difficult with Newtonian mechanics, we need generalization. And another thing is that, for example, if you get, say, for example, I will give you an example. For example, let us imagine that Newton's law, so you're solving for a vector quantity. Okay, 1, 2, 3, 4, 5, 6, 7, 8. But what will you do if you have n particles, n number of particles? So you get 3n or 10n and many equations. So how do we do with those number of equations? How do we deal with those n number of particles? So generalized coordinates often reduce the number of equation, because they only track necessary motion, ignoring the constraints. So as I told you, simple pendulum with a mass at the end, just one equation, the Lagrangian mechanics, instead of using the Newtonian mechanics. So we actually need those things in order to make things easier, much easier. Okay, I will just quickly show you what do I mean by this. So here you can see there are three things I told you: generalized coordinates, generalized momentum, and generalized velocity. Generalized coordinate, why do we need it? Simple, because x, y, and z does not happen. So we generalize to qi. That means 1, 2, 3, 4, 5, 6, n. So that would help us, instead of using Cartesian coordinate, we can use just one coordinate. Okay. Wouldn't center of mass also reduces? Yes, 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 Chudamani, right. Center of mass would also reduce in many particle system. It would become further complex. You are right, I can show that equation, but right at this moment, as I'm going with this agenda, yes, you are very right telling that it would reduce. Okay, what is the next? You see that classical momentum, if I use something which is called a generalized momentum, isn't it easier? Pi is the generalized momentum, L is the Lagrangian, and Q dot I is what? It is the generalized velocity with the time derivative of the generalized coordinate. So generalized momentum also can help us, linear momentum, angular momentum, everything is now in one place. Okay, and we get what is called a generalized velocity also. So unlike regular velocity, which is in meter per second, generalized velocity also depends on the choice of the coordinate. So q1 equals to x now becomes q1 dot equals to x dot. So the generalized velocity, which actually measures angular velocity in radians, etc., happens. So now, I hope that now things are getting clear to you, that why do we need those things? Okay, generalized momentum, generalized coordinate, etc. This is the reason we need. So here is a quick understanding of a little bit deeper in what we called is the generalized coordinates. Why do we need the generalized coordinate? Okay, let us see that. So here, what you can see over here is that I have just used this one, a simple pendulum, okay, which Chudamani was telling. He is right. Instead of x, y, and z, what am I doing? I am using the theta. So a double pendulum, a pendulum attached to another pendulum, can be described using theta 1 and theta 2, right? So they are generalized coordinate because now we are not restricted to any specific coordinate like Cartesian coordinate, and can represent any variable which describe the system's configuration, including angles, distances, etc. So bead on a wire, double pendulum, etc. Only independent degrees of freedom are used, reducing the number of equations. Here you can see what I have actually written. This is called the generalized coordinate. So say, for example, you take this box. Okay. In this box, we have how many? 3 degrees of freedom, x, y, and z. Simple pendulum has 1 degree of freedom. Double pendulum has got 2 degrees of freedom. So if a system which has got n degrees of freedom, n generalized coordinate, the state of a system is fully determined by the values of the generalized coordinate, qi, and the time derivative. So the Euler Lagrange equation are written in terms of I equals to 1, 2, 3, 4, dot, 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 goes on. So I hope now you can understand that why these generalized coordinates, etc., the values are becoming easier. And you can see that this dqi by dt is nothing but this is basically the generalized velocity which is coming up. So this is basically what I told you, the advantage. It simplifies equations of motion. It handles constraints automatically, what Chudamani was telling, and works in any coordinate system: Cartesian, polar, cylindrical, spherical, etc. So this is what is actually the difference. Now here you see that when we talk of generalized velocity also, here you can see what happens. In Cartesian coordinate, traditional velocity is what? It is very straightforward, dx by dt, okay? V is equal to dy by dt and so on. But in generalized coordinate, what happens in polar coordinates, you can see r dot is given by dr by dt. Theta dot is given by d theta and dt. And units may vary. So generalized velocity actually, I would say, inherits the units of the corresponding generalized coordinates. So if qi is for distance, qi is a velocity, qi dot is velocity meters per second. If qi is an angle, then qi dot is an angular velocity, and so on. Okay. So from here, what we get is this one. We can say that if a system is represented by q1, q2, dot, 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 up to qn, the system is fully determined by the values of the generalized coordinate and the time derivative, which are the generalized velocities. Time derivative means what? It would be velocity, distance by time. So it becomes generalized velocity. So understand that the term generalized is used because the velocities are not limited to traditional Cartesian velocities. Instead, they correspond to the rates of change of any generalized coordinates that uniquely describe the system. Okay, so that is why we go to get those generalized things. And here is a quick understanding what is the physical meaning. Physical meanings means generalized velocity is the rate of change of the generalized coordinate with respect to time. Simple English. So for particles in Cartesian coordinate, generalized velocity corresponds to traditional velocity. For a pendulum, the angle of direction, generalized velocity theta dot is the angular velocity. For system with constraint, generalized velocities are the rates at which the generalized coordinates changes in account with the constraints. And kinetic energy of a system is expressed as a function of the generalized velocity q1, q2, dot, 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 and it goes on. Right? Generalized velocities also appears in the Lagrangian. So finally, we can draw a kind of a summary, and we can say that generalized velocities are actually enables us the Lagrangian of the system. It works for any particular system, works for coordinate Cartesian and polar coordinates, and this is how it is crucial for deriving the equations of motion and so on. Now, from here, if we look in generalized velocity, things will become much more easier. Okay, so if you take a particle, for example, in a simple Cartesian coordinate system, for example, here you can see the particle, it has got x, y, and z. So if it is moving in three-dimension space, the generalized coordinates are q1 equals to x, q2 equals to y, and q3 equals to z. So the velocity is given by what? q1 dot equals to x dot, q2 dot equal to, and so on. And the Lagrangian is basically what? Kinetic minus potential energy. So T minus V equals to half of M x dot V. What is V? Potential. So we are substituting x dot squared plus y dot squared plus z dot squared minus V x y z. So the generalized momentum associated with the coordinate becomes this. And this is exactly the classical momentum, P equals to mv for the x component. Similarly, we can calculate for the y component, which I have not done over here. So ultimately, you can see nothing is becoming very complex. Ultimately, what is happening is that all of these things are basically getting reduced to what is called Newton's laws of motion. So that is why I always tell, yeah, I will suggest some good references. Don't worry. But who is this? Bhima Raju. But Bhima Raju, tell me, are you enjoying this session? I mean to say, is my all these efforts coming useful? Okay, what I am talking for about an hour, just let me know. So that is why I always tell, although I am biased, that Isaac Newton is one of the greatest physicists or scientists, because all these things ultimately boils down to Newton's laws of motion, and we are doing this either by okay, thank you very much. Thank you very much. So either we are doing this in this direction or in that direction or this. So here you can see we have added simply the kinetic energy and the potential energy. Enjoying from Turkey. Okay. Higher flows. Okay. Wonderful. Thank you very much. I'm so happy that my lectures have even reached Turkey. That's wonderful. That's amazing. So you can see that ultimately it is coming down and boiling down to one simple thing, which is basically the P equals to mv, or the classical momentum. So we generalized due to certain problems, but we have not done something extraordinary. What we have done actually is that we have taken all those things in particular to solve the equations of motion. Here you can see just quickly that this is generalized momentum. So in case of a generalized momentum, what we have done is this one. We have taken the generalized momentum and we have plugged in the Lagrangian values. Okay. So the Lagrangian generalized momentum is basically P equals to mv, and this is how it is defined. Anyway, I'm skipping this part, which might be a little bit technical. Now, you might be also wondering that why do we take the partial derivatives? Okay, why we are not taking the normal derivative. Now, why we are taking the partial derivative? Because in general, derivatives represent the rate of change. Okay, in the concept of Lagrangian mechanics, the generalized velocity represents how a particular coordinate changes with respect to time. And remember that what is happening over here is not one coordinate, not two coordinates, but many coordinates. So if I take 3, 4, or 5 coordinates, normal derivatives won't be able to do. So what we need to do? We have to take partial derivatives. We have to take partial derivatives. So for example, if we take the generalized momentum Pi associated with the coordinate Qi, it is related to how the kinetic energy of the system changes as the velocity changes. So by taking the partial derivative of the Lagrangian, for example, which includes kinetic and potential energy, with respect to Qi, what we are doing is that we are essentially isolating the contribution of that specific velocity component to the overall momentum of the system. I will give you a simple analogy. Think of this. Okay, think of this. For example, you have a car, okay, in 2 dimensions, x and y. The total kinetic energy depends on both x velocity and y velocity. If you want to know how the kinetic energy changes specifically due to change in the x velocity, you would take the partial derivative of the kinetic energy with respect to the x velocity, and this will give you momentum component associated with the x direction, keeping y and z intact. Now, taking the partial derivative of the Lagrangian with respect to the generalized velocity is a mathematical technique to extract the relevant information about the momentum associated with the particular degree of freedom. So, this process is fundamental to understanding the dynamics of the system within the framework of Lagrangian mechanics. Because we are dealing with so many values, then one normal derivative actually won't help us. So taking the partial derivative of the Lagrangian with respect to generalized velocity helps us to extract things. Now here this is the last part of our discussion. You might be wondering that this P equals to mv, where what we get, the classical momentum, can we get it from the generalized momentum or using the Lagrangians? Yes, we can do that. And here is a simple derivation, which I'm not explaining page by page. I mean to say part by part. What I have done is that I've just taken a particular particle moving t equals to half mx dot squared. If the potential energy V depends on x, I calculate the Lagrangian. We know the value of the generalized momentum over here. Okay, and using the generalized momentum we get this value, and we know since Vx, that is potential energy, depends on x dot, I calculate the derivative with respect to x dot, and finally what we get again is the classical linear momentum. So actually it tells us that our calculations are correct. Okay, so what is the overall summary we got here? We got what is called generalized coordinates. It helps describe in the most convenient way, right? The coordinates are now much more generalized, easier. We got generalized velocity, which is the time derivative of the generalized coordinate. Then we got generalized momentum derived from the Lagrangian. And all these three things are put into Euler Lagrange equation, which determines the system's motion, which naturally gives rise to from the generalized momentum part. No, this equation is PDE. It is not. It is not the what we call the ordinary differential equation. I told you, Bhima Raju, that ordinary differential equations won't be working because we are dealing with so many coordinates and we are getting a generalized coordinate. Okay. Now, Bhima Raju has suggested for some suggestions. So here is a book. Let me tell you the name of the book. The name of the book is Lagrangian Mechanics. You can go through this book. It is written by Lucio Prifoli, Lagrangian Hamiltonian Mechanics. You do one thing, Bhima Raju, you can just contact me later on my WhatsApp or email me, I will tell you the name of the books. There is one called Lagrangian Hamiltonian Mechanics. You can also look on my videos. I've given a very detailed idea of Lagrangian mechanics. So anyway, so that brings us to the yes, okay, Anjan, I missed Anjan Krishna's question. So is it like an average? No, it won't be an average. Okay, yes, you can think that to be an average. Yes, because overall it sounds like average, but it is more than an average. Because in average, we are not considering anything on a partial derivative way, etc. Right, Anjan? So average is to think it on a very easy manner. You can say, okay, this is an average, but no, it actually considers each and every particle, but instead of individual particle, it is taking what is called the total energy of the system. Okay, so it would be technically wrong to say average. Okay, but yes, it is a kind of an average, but it is not a complete average. How can I say this is average? This is Lagrangian. So overall, it connects not using the Euler Lagrange equations. So that is how it is. Okay, so lastly, what I would like to tell you, tomorrow again I will be coming live, and this time I will be talking about gravity, and either I will talk about gravity or quantum mechanics. I have not decided as yet. Okay, what I will do, got it. Okay, thank you. But what I will do is tomorrow, because I have got a live on the other channel. Do you know about my other channel? Okay, let me give this link to you all. Please be there tomorrow at 8 o'clock, because there will be a podcast with Astro Kshitij, who will be actually talking about black holes and singularity. Okay, so here is the channel name. You can be there tomorrow at 8 o'clock. So tomorrow I will be coming live around about 5 p.m. evening to 6 p.m. around about 1 hour. Either the topic will be quantum mechanics or gravity, Poisson equation, and general relativity, how it actually boils down to Einstein field equation. Either is that. Which time zone? Okay, so it is 9:03 p.m. Indian Standard Time right now. So Turkey, I don't know. Let me find out. Indian time 5 p.m. to Turkey time. So it is telling 2:30 p.m. Indian time, 5 p.m. to Turkey time. So it is telling it would be 5 p.m. You need to calculate higher flows. Okay. I mean to say, right now it is 9:04 p.m. night at India. So I don't know what time it is at your place. So let me find out Turkey time now. Oh, it is 6:34 p.m. your time. So that means if I say that, okay, let me find it out. India evening 5 p.m. to Turkey time. What does it give? So it is telling that you need to subtract 2 hours 30 minutes. So it would be 2:30 p.m. Yeah. It is 6:34 p.m. there, right? So it is 6:34 p.m. there, and it is 9 p.m. here. So that means, yes, roughly you can just calculate 2.5 hours. Right? So what it tells is 2:30 p.m. in Turkey. So tomorrow it would be 2:30 p.m. Turkey. Or what you can do is that you can WhatsApp me. I will just tell you my WhatsApp number. And what you can do is that I can tell you 30 minutes earlier when I am coming online. That would be better. Okay. You can just WhatsApp me at this number that, hi, I am so and so. I'll just tell you half an hour earlier when I am coming online. So if it's 6:30 p.m., 9 p.m., 2.5 hours. So 5 p.m. would be 2:30 p.m. Right? So thank you very much. Tomorrow we have 2 events. One, I would be coming live on this channel talking either about quantum physics or gravity. I have not decided, but again, it would be a very interesting session. And at 8 p.m. On this channel, which I have given you, there will be a very good podcast, interesting podcast on black holes, cosmology, and singularity. Thank you very much. Please do put up the comment if you have liked it once we end the session. And that would really give me a motivation to do this on and on. Thank you very much. Goodbye. Take care.